Hello and welcome to the next installment of the final exam review from CDLI for Calculus 3208. Today we're going to look at a further topic in limits and continuity, and we're looking at limits at infinity. So previously we looked at infinite limits, which are different. Infinite limits occur when x is approaching a finite value and the y values go way up in the sky to a positive infinity or way down to negative infinity. This time we're going to find out what happens to the values of y as x approaches infinity. So these are what we call limits at infinity as opposed to infinite limits. So let's get started. Let's look at some of the key features that we have to examine with this. And two of those are, the first one, limits at infinity of rational functions. And then we're going to look at limits at infinity and functions that deal with radicals as well. So we're not going to deal with graphing anything to do with this stuff today. That's in a future session. What we're mostly concerned with is how do we calculate those limits. So here are some rules for simple functions as x approaches plus or minus infinity. So we determine what we call the end behavior of the function by looking at two limits. The first one of which is as x approaches positive infinity, we see what happens to the function on the far right of the graph. And as x approaches negative infinity, we see what happens to the function on the far left of the graph, We call that the end behavior, one way or the other. So a couple of simple types of functions we should know about are, first of all, power functions, where we take x raised to some natural number power, like x squared or x to the power 5, etc. And basically, that's fairly simple. As x approaches positive infinity for any power function, we're going to end up with positive infinity for the power function. And as x approaches negative infinity, we'll end up at positive infinity if the exponent that we're dealing with, n, in other words, if that exponent is an even number, then squaring it will always produce a positive answer. And if that exponent is an odd number, squaring a negative will produce a negative answer. So if we're looking at that, we have sort of a twofold definition here. So the limit as x approaches negative infinity could be positive or negative infinity depending on the even or odd value of the exponent. We're also going to look at reciprocals of power functions real quickly now. So if I take any power function and turn it upside down, so let's say x to the power 5, flip that over, and I've got 1 over x to the power 5. Then whether x is going to plus or minus infinity doesn't really matter. Either way, the entire fraction that we have here, if the numerator stays at 1 and the denominator gets really huge, that's heading for 0. So either way, we have, with the reciprocal of a power function, our limit is going to be equal to 0. Okay, so let's get to some more interesting things. So let's look at the limit of a rational function. So basically, I've got a polynomial in my numerator and a polynomial in my denominator, and what I have to do is find out the limit, in this case, as x approaches positive infinity. So there's a basic technique that we use to evaluate these. So we look, first of all, for the largest power of x that we see anywhere in this expression. So right here in the numerator, the biggest power I see is x squared, so I have a power of 2. And in the denominator, I see x cubed, so I have a power of 3. What I do is I take this particular expression and I multiply it by this funny looking fraction over here, where n is actually the biggest power I see anywhere. So the biggest power we saw anywhere there was a 3. So all I'm going to do to help me evaluate this limit then is I'm going to take x to the power of 3 divided by 1 over x to the power of 3, and we know that multiplying any fraction by a fraction with the same numerator and denominator is just like multiplying it by 1, so we don't really change the value. We're just going to change how it looks to make it easier for us to understand where this function is headed as x goes to infinity. So now we're going to look at this limit as x approaches infinity. And so basically the idea here is I'm going to take this reciprocated function and multiply by each of these terms using my distributive property. So I end up with 5x squared times 1 over x cubed just gives me 5x squared over x cubed, minus the next term will turn out to be x over x cubed plus 17 over x cubed. And in the denominator, I'll do the same thing. Multiplying by that reciprocal just basically takes every term down here and divides them all by x cubed. So let's see what this is going to do. We're going to have x squared over x cubed, and then plus x over x cubed, and last but not least, minus 12 over x cubed. Alrighty. So now what we can do is we can simplify all that stuff, because a lot of those x's and sort of powers and all that stuff, we can reduce a lot of those fractions. So let's see where this is going to take us. So this is going to be 5 over x minus 1 over x squared plus, not much we can do with 17 over x cubed. We've got to leave that guy alone. And this will all be divided by 3, because the x cubes will both cancel out in this term, minus 1 over x plus 1 over x squared, and minus 12 over x to the power of 3. Alrighty, so as x approaches infinity, what we should notice is that a whole lot of these terms are going to one place in an awful hurry. 5 over x, 1 over x squared, 17 over x cubed, 1 over x squared, 12 over x cubed. As x gets really, really big, like infinity, any constant number divided by a really increasingly bigger number will always head towards 0. So all of the terms in my numerator here, if I look at this limit as x approaches infinity, are all going to head towards 0. And everything in my denominator except for this 3 also go to 0. So all I'm left with down there is 3. So as x approaches infinity, this limit is just equal to 0 divided by 3, or 0. Now that's our basic technique for rational functions. So let's look at an example here. Actually, we've got a couple. So the first one, the limit as x approaches infinity. So in this case, I see the biggest power of x anywhere in part A is 5. So I'm going to multiply everything by 1 over x to the power of 5 divided by 1 over x to the power of 5. So making that a little bit quicker than we did in all the gory detail of that first case when we went through it and all that detail, I'm going to say 4x to the power of 5 divided by x to the power of 5 is just going to be 4. And then I'm going to end up with minus 2, and reducing that one on site is going to give us over x cubed plus 3 over x to the power of 5. And in my denominator, I'll have 5 plus x cubed over x to the power of 5 will give me 1 over x squared. And then it's going to be 1 over x to the power of 4 minus 5 over x to the power of 5. So let's look at all the terms here that are going to approach 0 when x heads off to infinity. Well, this one, this one, this one, this one, and this one. So all of those terms are going to shrink to 0, and in the numerator we're left with just a 4, while in the denominator we're left with 5. So in the end, this limit, as x gets huge, is going to approach 4/5. So that's our limit for that one. Let's try the same technique on this next one. So over here, the largest power of x that I see anywhere is a 3. There it is. So I'm going to multiply by 1 over x cubed and 1 over x cubed. So what does that give us? Well, we have the limit as x goes off to minus infinity. And we're going to end up dividing every term by x cubed. So that'll give us 3 plus 2 over x plus 3 over x cubed, all divided by 2 over x plus x over x cubed is 1 over x squared plus 7 over x cubed. And let's examine all these terms to see where they're going to end up. Well, all of these guys are heading for 0, no question about it. So they're all going to approach 0, and my numerator is going to approach 3. So my denominator is going to approach 0. Looks to me like this guy is heading for, yep, probably going to be infinity or negative infinity. Hard to tell at this point, but what we can see here is, unless we sort of factor all this out and check out the details, either way, we're going to end up at negative or positive infinity. I can tell because of this dominant term, sorry, this one will be the dominant term, that we're going to end up at negative infinity. So, irrelevant. The most important thing there is that we're not headed for any finite value. Alrighty, so that's because we're heading through the right left there. Alright, let's check out what we have to do if, instead of just a rational function, I want to take the limit as x approaches infinity, only this time I'm dealing with x squared over a radical, the square root of x to the power of 4 plus 1. Well, this is kind of a trick that's sort of old hat for folks who've done calculus for a number of years, and it shows up in every calculus text where they do an examination of limits. What we're really going to do here is we're going to modify that same technique that we had so that it will work for this radical. And what you'll notice, if you think about these powers, on the top I have x to the power of 2. And on the bottom I have x to the power of 4, but if that's square rooted, a power of 4 square rooted is going to end up somewhere around 2. Well, what we do is I multiply the numerator by 1 over x squared, and I multiply the denominator by something that I know is the same as 1 over x squared, that being 1 over the square root of x to the power of 4. So what that does is it allows me to divide all my terms in the numerator, and in this case there's only 1, by x squared. So I'm going to have the limit as x approaches infinity, and it's going to be x squared over x squared, which is just 1 up top, and then in my denominator I'm going to have a square root of. So x to the power of 4 over x to the power of 4 is 1, and then plus 1 over x to the power of 4. So I've got 1 over x to the power of 4 here. So as x approaches infinity, this term heads to 0 in a hurry. My numerator stays at 1, and in the bottom, or my denominator, I'm going to have the square root of 1, which is also just 1. So that limit is 1, and that's pretty straightforward. All right, so let's try a couple of examples with those types of limits. So in the first one, we've got to pick out a power that we can make work for this. Well, the biggest power I see up top is a square, but that's square rooted. So roughly that's equivalent to a 1, so a power of 1, which is the power that I see down here on x. So what I'm going to do is I'm going to multiply by 1 over x on the bottom, and I'm going to multiply by 1 over the square root of x squared up top, so that I can actually multiply through by the radical, and these two things are really equal as long as we're dealing with positive numbers for x. And as we're going to positive infinity, we sure are. So let's see what we've got. We have a limit as x approaches infinity, and up top that'll give us a square root of 2 times x squared divided by x squared is just 2, minus 3 over x plus 7 over x squared. And then our denominator will be 5 over 5x divided by x is 5, plus we've got 11 over x. And as x gets really huge, these 3 terms I'm circling now are all going to head towards 0. And in the limit, all we'll be left with in the numerator is the square root of 2. And in our denominator, we'll have 5. So we get root 2 over 5 as our limit that time. Alrighty, let's look at this next one. Now this one is a little bit tricky. Basically the same idea. You might think, okay, I've got a power 1 here, power 2 here, but it's square rooted, similar to what we had in the first example. But we have to be careful. 1 over x and 1 over the square root of x squared are what we're going to suspect we have to take here. But we're approaching negative infinity. So we're looking at negative numbers for x, getting really, really negative. So 1 over x will always have negative values there because the reciprocal of a negative is a negative. But 1 over the square root of x squared will have the effect of taking the absolute value, because I'm going to square the numbers and then square root them. But the squaring process that I do first will make them all positive, square rooting to give me a positive. So really, the two things I have on the top and the bottom of this fraction right here are not the same. One is negative and one is positive. And I'm only allowed to multiply by something that's equal to 1 so that I don't change the value of my limit. So what we kind of do is we just cheat a little bit. We say, okay, let's make that negative 1 over x, and then we'll make it 1 over the square root of x squared in the bottom. And that's fairly straightforward. Then all we have to do is remember our limit laws. If I'm multiplying by a negative here, I can just stick that negative 1 out in front of my limit. So I have the limit now as x approaches negative infinity of 4 plus 3 over x. And we're all going to be divided now by the square root of, let's see, 2x squared over x squared is 2, plus x over x squared, 1 over x, and then 7 over x squared. Where's all this stuff heading? Well, that's going to 0. Oops, I forgot my plus sign there, excuse me. That's going to 0, and that's going to 0. So what I end up with is a negative outside of 4 divided by the square root of 2. So we'll quickly rationalize, multiplying by root 2 over root 2, and we get 4 root 2 all over 2. So in other words, it's negative 2 root 2. And that's where this function is heading. Alrighty. Let's take a look at a test type question, and this one is a multiple choice question. It says, which limit has a value of 3/4? Well, we could work them all out, but if we remember what we saw in a previous example, then whenever these powers are the same, and I divide by 1 over x, or multiply by 1 over x squared, and then I'm dividing by x squared, the only one that's going to give me 2 of those guys left in the end will be part B here. If those powers are not the same, one of them is going to head to 0, and I'm either going to end up with a limit of 0 or a limit that's going to give me some undefined answer like positive infinity or negative infinity. So the answer here has to be B. We'll get into more detail about that when we get into finding horizontal asymptotes in a future section. Alrighty, the next one says evaluate this limit, and it says as x approaches negative infinity here. Well, there's kind of a big rule here. As long as we're dealing with just a rational function, as long as it's just rational and there's nothing crazy going on, in other words, there's no radicals or anything like we saw in some previous examples, then the limit as x approaches negative infinity of that function will be equal to the limit as x approaches positive infinity of that function, as long as it's rational. So I'm not really worried about this negative infinity business at all. It shouldn't affect anything I do. So let's see what's going to happen. If we take the limit as x approaches negative infinity here, I'm going to have to look for the biggest power of x I see, which is 1 over x to the power 4, divided by 1 over x to the power 4. And when I multiply through, I get the limit as x approaches negative infinity, and that gives us negative 3 over x squared plus 2 over x cubed plus 5 over x to the power 4. And it looks like no matter what's happening down on the bottom, as long as it just gives us a 7 there, and we end up here with 5 over x squared, 1 over x to the power 4, but none of that really matters. It's all a moot point. All of this stuff is 0, so I get a numerator of 0 and a denominator of 7, so we're headed for a value of 0 here. One way or the other, doesn't really matter. Okie doke. So those are your two sample test type questions. Here's the or turn question. It's one of those tricky radicals. Have some fun with it. Pause the recording now if you want to try it. I'm going to jump to the next slide. Here's the solution. So you can have a read through that. There's some good detail given there. And finally, here are the key ideas that we discussed in this session. So when we're looking at the limit of a power function, as long as we're going to positive infinity, we head to positive infinity for y as well as x. If x is going to negative infinity, then it depends on whether the exponent is odd or even. And if we take the limit as x approaches either plus or minus infinity of the reciprocal of a power function, that heads for 0. If we want to evaluate the limit of a rational function, we use this funny looking multiplier here to sort of even the odds and make it understandable. And in the case of a radical, we modify this multiplier to become one of two things. We either say 1 over x to the power of n and 1 over the square root of x to the power of 2n, so like our x squared and x to the power of 4, or if we're dealing with negative infinity, we have to tuck a negative in front of at least one of those, or only one of those, in order to make all that work out. All right, so there's a quick review of how we evaluate limits of rational functions and of square root functions, or basically what we call limits at infinity. So good luck studying, good luck with your exams, and hope that was helpful.